Good afternoon, everybody. So this is the start of the ESA session. I will introduce myself and my colleagues who contribute to this session. So I'm Francesco Sarti from ESA, Earth Observation Directorate, and I'm in charge of the coordination for the training activities, including polarimetry. And also I'm managing the polarimetric community and PolInSAR conferences. By the way, that's the place where we met for the first time with some of your Indian colleagues from ISRO, and that's how it so started. They invited us here, and hopefully this is just the beginning of a series of joint activities in polarimetry. Then Magdalena Fitschik, sitting there, the name is misspelled, my fault, and Klaus Kippel. They will speak after me, so we will try to give you an overview of the state of the art in polarimetry in ESA in Europe for the last 20 years, and also the activities that we perform in training, capacity building, education, in remote sensing in general, and in radar polarimetry, and also what is the status of our forthcoming polarimetric missions. First of all, Biomass, and Klaus is the best person here. If you have any questions about the Biomass mission, he will be able to reply to every scientific question that you have, and not only scientific. And then our distinguished professors, Carlos and Armando, will continue and give you also in the end, they will explain again the basis of polarimetry on top of what Carlos already showed you. And finally, there is also a demo based on Python. And yes, online, on top of ourselves, there is also Rena Heinzek from DLR and ETH Zurich, who's a very good scientist in radar polarimetry, and she's going to present remotely. So I will start with a very quick overview of the state of the art in polarimetry and the main achievement that we had. Of course, that's for whatever the 15 minutes that I have allow me to do. So how did it start everything 20 years ago in ESA? I call it the genesis. We started in 2023 with the first workshop in polarimetry that was based on the fact that we had some studies, contracts about PolInSAR, polarimetric SAR, managed by my previous boss. And it was very promising, so we decided to have a first workshop, and there were many people coming, many more than we expected. And so this was just the first series of the first one of a series of workshops on radar polarimetry called PolInSAR. We are doing them every 2 years in Europe. Initially it was just in Esren, now we are doing that in different cities. And there we gather all the scientific community working on polarimetry, and not only from Europe. So everybody is invited to take part. We had in the last one, there was Geoscience from ISRO, and hopefully there will be many more in the next editions. So the purpose of this workshop was to promote the scientific exchange in the polarimetric community and SAR community in general, to present the ways geophysical parameters can be retrieved from SAR and from PolInSAR, also assess the available tools, demonstrate the latest techniques, and also gather recommendations for future studies and for future missions. Of course, the first comment that we get and we keep receiving since many years was that how can we really push the development of these techniques and these methods if we don't have polarimetry data, space-bound polarimetric data in Europe. And it was a correct comment. So for many years, we had to deal with the airborne campaigns. We had to use data from other agencies, so mainly Japanese with ALOS, and then Radarsat-2 and others. And now we are finally in the position almost to distribute the first ESA polarimetric mission data. So it will be in 2025 with the Biomass launch. And we are also preparing for other polarimetric missions like Rosen and Sentinel-1 new generation that we have. Of course, they will not provide only quad-pole data, but they have a quad-pole capability. But it took 20 years. So it was a long time. So how did we proceed in these 20 years of polarimetry? We started to develop initially a tool called PolInSAR Pro that many of you use in India. We are very happy to find out that there is such a large knowledge about this tool and a large use. That was done mainly by our professor in France, Eric Potier, who was really the father or one of the fathers of polarimetry, and for sure was the father of this tool, which is still being used and distributed by ESA. By the way, now we are implementing a Python version on it that will go on the MAP platform that you probably already heard about, because it's the platform where the ISAR and biomass data will be made available for use and processing. So we had initial cooperation with JAXA, with the Japanese, for the ALOS data distribution. So we did the announcement of opportunities to distribute ALOS data to European users. And we started also 2 years ago the first polarimetry course that was associated to PolInSAR. And now every time that we have PolInSAR conference, the week before we have 1 week of training, physical training about polarimetry. This is complemented, by the way, now by the online training courses done by DLR on polarimetry. DLR is the German Space Agency, so I have to do quick. And I think it's open, by the way, to everybody. It's not only for Europeans, so you're welcome to apply also for those courses. And Klaus can tell you more about those. Then we had many airborne campaigns. Also we started distributing the RadarSat-2 data together with the Canadians. Then in 2014 we had the Sentinel-1 launch, which was not a polarimetry mission, but still has a dual pole capability. So it's I think it's being used largely also here in India. I heard by, for example, Professor Avik using those data a lot, but we still, of course, had the need of a dedicated PolInSAR mission. And also, what is being told all the time by the scientists, that there is a need for dedicated PolInSAR dataset with simultaneous ground truth. So that's a very important requirement from the community. We try now to fill that gap also with the help of the CEOs working group on visual constellations, but it's still an issue. And if you can help us with this, this would be very much appreciated. It's a ongoing action of the CEOs and also the polarimetry community. And finally, the last PolInSAR that we did last June was a big success. We had finally also many young people, because for some time this polarimetric community was a niche of professors and the experts, but we want to welcome more and more young people into this field. And of course, this will be really achieved only when the data are available. This I am fully aware. So we have India participation in the PolInSAR conferences, as I said. We had about 20 participants in the last PolInSAR editions. And by the way, India is the second largest community in the world for Sentinel-1 data. And also the second biggest user community for Sentinel-1 data on the ESA data hubs, and the seventh most prolific community on publications on Sentinel-1 data. So what were the main topics covered in the last conference? And I'm saying that not because I want to promote the conference, but because these data are available to everybody. So we publish this data, and for me, it's a sort of reference for the latest results in polarimetry. So if you want to look at the state of the art of polarimetry, you could download the presentations from this conference. Most of them, maybe all of them, are also available via videos, and it's really a good reference for the state of the art in polarimetry. So we try to cover the methods, tools, also calibration, validation, and applications. And on top of that, we had also some parallel sessions on biomass that were organized by Klaus. So in long applications, we covered forestry, agriculture, wetlands, and soil moisture. We also had pollution, for ocean applications, pollution, ship detection, retrieval of parameters, cryosphere applications, so snow and land and sea ice, and finally hazards, for monitoring volcanoes, flooding, and earthquake. So a few examples or applications that I mentioned for forestry, for example, we have forest size estimation, biomass estimation, 3D structure, tomography, biogeophysical parameter retrieval. So if we compare from to the beginning, we had initially just a few studies based on urban data back to 2003 about forest site estimation with a single baseline PolInSAR data. And we can now exploit thousands of pandemics data. So with 12,000 pandemics data, there was a very good estimation of a forest height over Amazonas. The data were compared to JEDI data, and the correlation was extremely good. For biomass and height map generation, also there was a proposal done 20 years ago by, I think it was Tulit and others, to develop a dedicated P-band mission. That is the biomass mission that is going to be launched in 2025, and that was based on PolInSAR capability. And finally, we got close to the launch, but Klaus will discuss that more in detail. So in 2013, there was the innovative proposal of using the SAR tomography technique to map 3D structures of forest. And initially that was done using airborne thermostat data in Guyana. And also in 2016 and 2019, high range biomass or typical forest with thermostat data was attempted and successfully succeeded, and also isolating different components of canopy, ground, and topography. Going to a different type of application for glacier and so ice and snow. Also, there were papers showing results about snow cover, what the equivalent snow depth, and also the use of PolInSAR and tomosar for glacier subsurface characterization, which was very nice. So go back to the prehistory. So in 2003, there were a few studies of cultural behavior of ice. And then in 2011, there were the first models developed to retrieve ice parameters. And currently, polarimetric tomography is really very powerful tool also for this type of applications. It was a very nice tomosar for glacial subsurface characterization that was done in 2021. And here there is a nice animation showing how tomosar can map different sublayers over the glacier down to 50 meters below the ice surface. Another example application for ocean is ship detection. And Armando here can tell you much more about that. Armando Marino. So in 2003, there were a few papers exploring quadpol for ship detection, mostly based on the selection of the best channel. And then in 2006, there were first interested towards the use of quadpol data. And nowadays, quadpol data use is shown to be outperforming for ship detection, and we are even starting to use machine learning on top of quadpol data to increase the accuracy of the ship detection, and also to manage the huge amount of available data. So what is very important, of course, for polarimetry, as I mentioned, on top of developing the tools and the techniques, is to have data availability, because otherwise we cannot really trigger the interest of the large user community. So initially we had to use airborne data sets. We had a few data sets in 2003 provided by DLR, and now there is a huge amount of excellent and well-documented data set, which include also ground measurements and LiDAR. All the excellent PolInSAR or tomosar data, like BISAR 1 and 2, TROPISAR, AFRISAR, INDEX 1 and 2, and many others. Thanks. So for satellite data, of course, we don't have such a rich data set. We had the use of ESA third-party mission, so which are cooperating agencies providing data to ESA for use to distribution to ESA users, including ALOS-1, PulSAR, and RADARSAT-2, and many other campaigns. So now we also have a cooperation with CONAE to distribute to European users the SAOCOM data. This is maybe not so relevant for you because we cannot distribute SAOCOM data to non-European users, but they could be interesting, something we'll discuss tomorrow with the ISRO colleague, to see whether this type of model could be extended also to India, because I think that you could benefit from the availability of SAOCOM data. So we should explore that tomorrow. So I don't know if you have questions. Otherwise, I will hand over to Maddalena for the training and capacity building component. Yes, please. Wait, I will give you the microphone so that everybody can hear.
Yeah. Are the data available with the raw data or directly the images that are already constructed?
Are you talking about the airborne data, the airborne campaigns?
The PolInSAR data, the Sentinel data, which you mentioned.
Oh, for Sentinel data. So I think you can order the raw data directly if you wish, but most users, of course, are downloading the level 1 data. So most is SLC, GRD data, ground range detected, and SLC, of course. But for the raw data with Sentinel-1, I'm not aware. For ERS, of course, it was the case, and there were people that were processing the raw data themselves. For Sentinel-1, I'm not aware if the raw data format is available for download. I can take the action and find out. We can exchange our emails. Of course, I am not able to answer all the questions about the technique that I've been showing so far because they come from the scientific community, but please ask the questions because Armando and Carlos are there and they can also help us. Armando, do you know about the raw data for Sentinel-1?
Yeah.
I think you should be able to do it, but I've never done myself, so I won't put my hand on the fire, as you say. But I think you are able to select which type of data you want, SLC or GRD and so on. And there is raw is one of the options. So level 0 is one of the options, I think.
So if the option is there, I should be possible to do it.
I think so. I think so.
Number 2, we said downloading data. Yes. So if you download from Alaska, did you get a database from Alaska?
No, I think the statistics are only from our hubs. So maybe you are the first one in the world. Who knows?
We should add the statistics of Alaska and put them together. Then we would have the overall statistics.
And that is also hosting all Sentinel data because we have a separate hub. From there, we will access and complete India. We are putting at our Bhunidhi server. So I think you have to get the statistics from there also because most of the people are Indian users to reduce that bandwidth and the tag. So we are providing the Indian data to the users through Bhunidhi. So okay. Sentinel-1 we can access from our server. So that statistic also should be used because we come to the first.
So you have an Indian facility to distribute
yes,
Sentinel-1 data.
Yeah.
And Sentinel-1 also Sentinel-2?
Both are there.
Both.
Optical and SAR we have, so they can download from that.
Very good.
Yeah.
So most of the time, though, like PolInSAR data is used for height estimation or for forest height estimation. So what advantages the PolInSAR data have compared to like other techniques like tomography or maybe LiDAR-based techniques?
So if I understand correctly, the question is what is the advantage of using the
PolInSAR data
for forest height estimation compared to other classical or traditional techniques?
It's also the like data is required much more now for estimation of height. So like what are the advantages of that?
Mm-hmm.
And if I want to apply it for, let's say, crop height detection, so like, how can I go for it?
So, well, first of all, with assuming that we had spaceborne missions, of course, you could use that much more easily and widely worldwide compared to campaigns that which are just on specific regions. Now, I know that campaigns have been compared to polarimetric capability, and the correlation is very good. But don't know, maybe Klaus can add something on that. So why go to polarimetry for side estimation if there are other techniques?
So I don't know. The only other technique that comes to my mind is LiDAR observations. Of course, with LiDAR, you only have a sample strategy. So you observe one spot, then you move by a few kilometers, observe the next spot. So you don't get a continuous map and you don't get a wall-to-wall map. So with SAR, you really get wall-to-wall information, which is quite important. The second thing was your question about agriculture. I think it depends very much on the frequency. So we have at the moment Biomass, it's the upcoming PolInSAR mission, but P-band, I think, has no sensitivity to agriculture. It's really made to observe dense forests. So you will not see a lot of agriculture. You can maybe do something with tandem X-band data. I think is very suited for agriculture. And I think there is examples in the literature available that are doing this. Southcom is L-band. I'm not sure you see a lot of agriculture there. So it depends really on your frequency and to which elements the frequency is sensitive to. Thank you.
We can probably give you a better answer once that we have the data available. I don't know if somebody has been testing already the Southcom data for that, for example, but as Klaus said, L-band maybe is not the most optimal.
Hello, thank you for your presentation. I am using the data of FSAR and TropSAR, I guess, from your hub. And I do not know, I mean, I forgot the data once I downloaded and I was trying to download the data from your hub again. And it was showing me that the user has exceeded its limit to download the data. I mean, is it a bug or have you fixed this number of downloads for one user? Do you know the answer?
Klaus can hopefully answer the question.
So drop me your name and I will make sure you get the data. I think it's not a bug, but it's probably a system setting. The platform we have set up is a demo mode. And maybe therefore there were some restrictions on how much data people can download, but we can easily fix that.
Okay,
yes.
okay, thank you.
So the answer, you should get friendly with Klaus.
But in future there will be no, I mean, there might be some limits, of course, for heavy users, but for normal science users, there should not be any limits.
Anyway, in the future, it will not as well, no? The campaign thing.
Yes. Okay, so maybe we have to move to the next presentation because we need to respect the time. Yeah, Irena will be connecting online at a certain time.
Okay, thank you, Francesco. So in my presentation, I would like to show you some of the activities of ESA regarding education training. So some activities on education and training and also international collaboration in SAR polarimetry, but not only, because I want to also show you some examples of our materials and trainings and processing platforms that on which we are not actually dealing with the polarimetric data, but I think it's a good example in general to be shown. So the activities that we are doing in the area of education and training, I divided them here in 5 groups. So first of all, the advanced courses, then I will explain you more in details each of these points. Then, of course, the massive open online open courses, MOOCs, development of educational software, data processing platforms, and different virtual laboratories that we are developing. And at the end, also dissemination of different online materials. So first of all, about trainings. Here, I'm showing the specific example of polarimetric training, but we have a lot of different trainings. We call them advanced trainings. Why advanced? Because let's say we are participants are starting from level of maybe last years of masters, PhD students, postdocs, and but also higher level, let's say, specialists and scientists. These trainings are divided into, say, thematic groups. So we have trainings related to specific applications, for example, land trainings, cryosphere, atmosphere, and so on, and also techniques. So we have one advanced training on SAR polarimetry. We had one training, I think, on hyperspectral data. No, interferometric training specifically we didn't have as an advanced course, at least. So here is an example of this training on polarimetric training. We call it polarimetry training. Usually these are like 1 week courses. We organize it every 2 years. The main objective is, of course, to train the new generation of Earth observation scientists. We explain both theory, so all the theoretical principles. We also show the tools and methods in different applications. So in case of polarimetry training, of course, we are showing the basics in radar polarimetry, polarimetric SAR interferometry, and tomography. And since last edition or the previous one, we are also introducing the Biomass mission and data and possible applications. So last training that we had was in Toulouse in this June. It is, as I said, series of trainings. You see, this is 7th training, but we organize it since 20 years. Until 2021, this course was supervised by organization of the course was, from the scientific point of view, was supervised by Professor Eric Bautier. Now we have a new generation. We have Armando, we have Carlos, and more fresh blood in polarimetry who are supporting us in the organization of the course. This course was historically, let's say, and so far we were always doing like that, was associated with the PolInSAR workshop. So it was just before PolInSAR workshop or just after, to, for the people who are coming for the PolInSAR workshop, maybe some students to stay for the course and vice versa. The very important thing is that all these advanced courses, we are collecting all the materials, data sets, presentations, and nowadays also, since few years, we are also recording videos, and these materials are all available on our website. So here, for example, is here is the PolInSAR, but maybe before I had also the link to the training. So all the materials are free for everyone, so you can go there, you can rewatch the videos at your own time, when you feel you need, maybe you have some time to expand your knowledge, you can study it. So this is all available, but of course we are inviting you also to apply for the next courses that will, next one will be 2025, so you are invited. And yeah, usually we are also giving data, some Jupyter notebooks, and important thing is that these courses are for free. You just need to come to Europe for the course, and we don't provide any student grants, unfortunately, but the course is for free. So I think it's already a very good thing. Yes.
So the philosophy of the ESA training is that the courses are always for free. We never apply a fee to students, but of course there is a process of selection. Normally we limit the participation to 20, 30, 50, okay, in this case even 50, but of course you have to pay for your own trip and accommodation. The other thing which is we always do is to use free data and free tools, so that the exercises can be redone by students when they go back home, or those who cannot attend the course can redo the exercise. We never use commercial software. So in this case, we use Python and PulsarPro, I think.
Okay, so in the domain of polarimetry, we have also another series of courses, and these are purely online courses that are organized by DLR and ESA in collaboration. I put here a link so you can go there. Now there is one course that is still ongoing. It's a few weeks course that the participants are joining for, I think, 2 hours, 2 times per week to the course, and they can do the exercises on at home, let's say, and then they are meeting with the scientists to discuss the results and also to have some lectures on about the theory. Now is the 6th edition. We have approximately 2 per year, and the next one will be in spring 2024, more or less. We didn't have so far many applications from India, so you are really invited to also apply for this course. There's always a selection because we need, I don't know, Klaus, how many people we accepted last time? For the DLR? 40 people. Yeah, it's the same. The selection is just to have more or less similar level of participants. It is easier for everyone. So the future training perspectives in PolInSAR, of course, we are planning to reinforce the cooperation and the coordination between these trainings, ESA, DLR, and so on. Then we have a Biomass initiative. This is an initiative, a collaboration with the CONAE, so the Argentinian Space Agency, and we would like to organize joint training activities in the frame of Biomass, especially focusing on SALCOM data. Then, of course, in future, when the biomass data will be available, for sure, we would like to provide training for the academic and scientific community. We think that there's also a potential for ESA and ISRO to cooperate and maybe organize similar training activities in this field, but of course, we have to discuss it further. Also in the preparation of the biomass mission data exploitation, there are already some existing materials like the ESA SAR MOOCs on the massive online open course. I will show you in the next slide as well the other courses, but this one is the SAR course, Echoes in Space. It is already existing. You can, of course, join to this MOOC. This is not, I say, it doesn't have any expiry date. You can just join it and use the materials. In the future, we want to update this MOOC and include more content about SAR polarimetry and related missions like SALCOM, NISAR, and maybe also RISAT satellites.
So I really invite you to have a look at this MOOC. It's different from other existing MOOCs because normally these MOOCs are running for a limited period of time, so a few months or 1 year. This is ongoing since almost now 4 years, and we plan to keep it online so people can register on the time, and then you have your own time to complete the course and to get the certificate in the end. And as Magda says, so far this MOOC is mainly about SAR theory and applications, and it uses Sentinel-1 and RADARSAT data. But we are starting already to have the next edition, which will be focused also on the biomass mission and other missions, including polarimetric missions. So there will be also focus on radar polarimetry. It would be nice to include also the RISAT series, so US04 data, and to have some examples and exercises based on that. So that's something we might do.
Okay, so apart from this Echoes in Space, the SAR MOOC, we have also other MOOCs. So if you are interested in optical data, or so we have this Land in Focus MOOC, we have Towards Zero Hunger, and there's also one upcoming about the data cubes and open data science in general. So this is something that is worth checking.
So the SAR MOOC is about the SAR technique. The land is about land application using combination of different sensors. So there are optical and radar data for applications about land.
So toolboxes that we are developing, Francesco already mentioned PolSAR Pro. As he said, many of you know already the software. So the software has a really long history. Now we are the version 6, and this would be rather the last version. We will be only updating this with some bug fixes and maybe some small additional features. We are now moving towards Python implementation. Since in 2021 in PolInSAR conference, we had a recommendation from the scientific community to implement some of the routines or possibly all of the routines of PolSAR Pro in Python, because at least in Europe, scientists are using now mostly Python. All of the students are studying Python, and I mean, all the young researchers are switching to Python. So we have now a contract with the company who is implementing these routines in Python. We have, of course, the scientific support of Professor Potier and Armando for, let's say, the scientific support, and they are also checking the performance and the quality of the results with this Python implementation. This Python code probably, we hope, when it's done, can be added, integrated to the ESA NASA map platform. For sure, I said, for sure. So, okay, this is just a bit, maybe a few more words about that. So, the idea is to have this dedicated Python library, polarimetric library, and it will be installed on the ESA NASA platform. And currently, as you see, we are moving from this C version that is used by many people already in the world to this PolSAR Pro Python library. Other toolbox that is maybe even most well-known toolbox of ESA, SNAP toolbox, especially if we're talking here about the polarimetric community and SAR community, the part of SNAP, which is the microwave toolbox. Now it's all integrated in one software, but okay, let's say the radar part. We are, of course, supporting full data from variety of sensors. We are providing basic functionalities to process quad-pole data. We know that also some of the Indian colleagues added their some of the algorithms to be injected to SNAP. So that is very nice. And of course, we can also use SNAP. In the past also we were even using PolSAR Pro. Maybe you are missing the geocoding part. So we know that there are some people who are bridging between PolSAR Pro and SNAP, at least for the geocoding part. So of course, SNAP also has optical part, so you can process all the sentinels and not only. So this is a very, very powerful tool. And by the way, we will have now a version 10. So yes, indeed, we don't have so far. We don't have in SNAP reader for EOS04, but we hope that in the near future we will also include this. So also for not only for Indian users but also for European users to use the Indian data.
And for this, we need your help, so you can help us. You should help us.
You should help us. Okay, so apart from these softwares, we have also a lot of platforms. There are some platforms that are only providing the access to the data. So, for example, Copernicus Data Space Ecosystem that I will show you in the next slide. We have also Open Science Catalog, but we have also platforms that are visualization platforms, and you can process some data. You can do some simple processing, but you can also you have also platform specifically dedicated to cloud computing, like OpenEO platform or Eurodata Cube, and we have also some services like the Tropical Cyclone Monitoring Service that I will show you also in the next slides. So very important news for all of you who is using Sentinel data that probably already know if you are using it regularly from our hub, that we used to distribute data through the Sentinel hub, and now it changed, and now we are distributing data through the Copernicus data space ecosystem. And this data space ecosystem is not only a platform to distribute the data itself, but also the orbits and all the auxiliary data. And it will also have, it already has some processing capabilities. So you don't have to move between different platforms, but there will be some also possibilities to process already data on the Copernicus data space ecosystem. So this is a big change for the users for sure. Of course, you can query the data using OpenSearch or OData or through the API. Then there is this Open Science Catalog, and this catalog is also very interesting. It is public, of course, publicly available catalog with the Geoscience products, data sets from our R&D projects. So you can search their projects of R&D projects and some results. You can have some reports, documentation of the projects. So I think it's also very interesting because it's all divided into different domains. So if you are specifically interested in the domains, you can also update yourself on the state of art of what other scientists are doing in the domain. Then there's an EO browser. EO browser is a very nice tool. We use it, for example, we use it also for education, because there is a specific mode of the platform, is educational mode, in which you have some tutorials already, some things implemented specifically for education. So you can use it to teach students. But you can also, for example, there are some ready-to-use band ratios for visualization. So it's just a fast visualization. For example, if you are not sure if the data set is okay, or I don't know, maybe you don't want to download data if it's too cloudy, maybe you want just to check data before. You can always do it also in your browser and visualize it easily. So it's good for the beginners, especially for the beginners, not only for schools.
Well, in the beginning, it was just purely visualization, a catalog of visualization. Then we remarked that having something which is web-based is much easier to use for beginners and for school teachers. So we got the request to modify this visualization tool to make it able also to do some processing. Of course, we cannot do interferometry, we cannot do stereoscopy, but we can do a lot of processing which is useful for the beginning applications. So, for example, you can include also your own tool to combine bands with mathematical. Yes, you can combine create your indices by combining some mathematical combination of the bands. So it's much more than just a visualization tool. So now we are using that extensively in Europe for school teaching in high schools, and also some universities in the first year they're using this as an introduction.
Okay. Now a bit more advanced tools, also used for visualization, but also not only for visualization, but you can also do some, say, small processing of the data. We have the Ocean Virtual Lab. We have Atmosphere Virtual Lab, so you can visualize their atmospheric Earth observation data, create some 2D and 3D plots, and you can analyze basically the data using the ESA's atmospheric toolbox. This is another toolbox specifically for the atmospheric community. We have the World Serial, a platform that is basically a cropland map, global cropland map at 10-meter resolution. So you can also visualize the results. It's still ongoing project, so not all of the results are there, but it is still nice to see, or at least to see how we are doing that. Yes, yes, it's global. Of course, it's yeah. We have also this Green Transition Information Factory. This is a platform that is specifically designed for decision makers, for industry, NGOs, citizens. So it is simple, and it's simple to create different reports. For now, the project is only done for Austria, but we plan to extend it over other countries. But this is a very nice tool, in fact, for all the decision makers and governmental institutions who want to really fast obtain some reports and some maps visualization. For
very user-friendly environmental monitoring and managing tool. But the data have been ingested now only for Austria.
Then we have also the world emission tool. We have Agriculture Virtual Lab, and here we have also Jupyter service. So we have a Jupyter Lab interface where you can integrate your own Jupyter notebooks. And you have, of course, the visualization service and explorer of the data. There are also some systems from our other projects integrated, like Send4Cap, Send2Agri. These are really focused on the agriculture. Then EuroDataCube. These are already more advanced processing platforms, which are providing also analysis-ready data. So we have the EuroDataCube. It gives access to commercial and public data, and you can process massive amount of data on the fly. And the same is with OpenEO platform. Here you can also, it is similar, let's say, in the concept, it is similar to the Google engine. Of course, we don't have this large community still, but the idea is more or less the same, to share different algorithms, and you can do it in R, you can do it also in Python and JavaScript. And of course, it has access to all the data collections. So again, you don't have to download anything. You can simply do it on the platform. And this is still an ongoing project. We want to also use it for education, by the way. So
among the data cubes, there are also some which contains not only Earth observation data, but also geophysical parameters, which are already retrieved. And you have the space and the time domain. So it can be very useful for applications for end users.
What else? We have online materials from past courses. So what I said already, from the advanced courses, you can always use the link that I showed before. You can download all the data, all the materials, videos, and so on. But there are also some online materials on YouTube. For example, we had this course. It was in 2021, I think, 2022. RSET that we organized. It was ESA NASA course on agriculture, a webinar, a series of webinars. There were yes, okay, and we had the session also in Spanish, and this is also available on YouTube. So if you just Google ESA NASA RSET agriculture webinar, you will find all the materials online.
By the way, there are also lectures about polarimetry application for agriculture there.
Yeah. The book that Carlos already mentioned before, published in 2021, that is also a very nice resource for you, especially for people who are starting in polarimetry and want to learn a bit more about the different applications. And the last point that I want to tackle is the international cooperation and capacity building. So, as I said, we are not only focused on education and training activities, but we also have many initiatives in the international cooperations. for training and capacity building. So we are part of the CEO's working group of capacity building and data democracy. So I think ISRO is also part of this working group. There is Director Senthil Kumar, that is a representative of ISRO. And this is basically a group of people from different agencies that are working together to organize capacity building events and different training courses, and also promoting training of common trainings, and not only common trainings, but also trainings organized by NASA, ESA, and other agencies. Then, of course, the project that we mentioned before for promotion, utilization, and mission applications in science, PUMAS, that is initiative together, ESA together with CONAE, so the Argentinian Space Agency. And within this initiative, we are distributing SALCOM data to European users, and we are also planning to do some training activities. And we have also other regional initiatives with other countries, and we are focusing there also on capacity building and training, and then sharing the data, sharing the knowledge and materials. Yes, Francesco, maybe last word.
Yeah, so I'm the ESA representative in the CEO's working group on capacity building, and there are so Senthil is representing ISRO. As far as I remember, there were no trainings organized for India by this working group, but you could mention to Senthil to make the request, and it would be very nice to have a joint course together, for example, with ESA, NASA, DLR, and CONAE. It would be very nice to organize a course here about the exploitation of SAT data and polarimetric data. Yeah, so please talk to Senthil.
And I think it was the last slide. So thank you very much. If you have any other questions, I don't know how you are sharing these presentations and if it's available for you, because there are a lot of links that may be useful for you to reach the materials. So I will leave it to the organizers, and then you can, I hope that they will share with you. And anyway, if you have any questions, we are here still.
The last thing you have.
Yes, we have. There is an archive of. We have a full archive of ERS and NVISA data, of course. How to make a request? Okay, but there is so. There were some changes in this, also in this archiving, in archival of old data sets. And I think for NVSAT, you have to write, it's called the proposal, but it's really like few sentences just to say how you are going to use the data. But this is really like a simple thing that it's maybe, you know, and in one day you will have access to the data. So this is simple.
Concerning the book that was presented by Maddalena and Carlos before, we could send you some sample copies. Well, not hundreds, but maybe a few tens. And we will need just one interface, maybe AVIC, and then to distribute it to different universities.
Yeah, I see. I'm reading it, but because there is a bit before one more. How SNAP tool can be used for soil moisture measurement? And this is a good question. The big question of the community, soil moisture measurement, always is appearing always. Well, there are some tools in SNAP. There is not specific, let's say, toolbox or a tool, since, as I said, this is still an open question. But I think all the basic SAR processing capabilities that exist in SNAP can be used. But yeah, there is no specific toolbox, let's say, for that. And then the next one, do you have any tool for polarimetric calibration so as to estimate the biases and correct them for sensor other than Sentinel-1? Which is us. This question, maybe you don't see it. Maybe Carlos or Armando, you can answer. You know the question? I will read it again. Do you have any tool for polarimetric calibration so as to estimate the biases and correct them for sensors other than Sentinel-1?
As far as I know, no. There isn't.
I'm not aware, but maybe you have something, or Carlos has something to say.
Okay, for calibration, there is a tool. I mean, because I did it. PolSAR Pro has some capabilities to check the calibration.
Okay.
It cannot calibrate itself because together with Eric, we didn't want to enter into the calibration because really you need the information of the systems. Okay, it's something. So PolSAR Pro is able to handle all the systems, but there is a tool to check if the data is properly calibrated. You can check on point targets and you distribute the targets. So one of the menus is on polarimetric, on checking the polarimetric calibration. Thank you.
There's also another question. Which resources can be used for further experiments? I don't know which experiments. Maybe the person who asked the question can specify. Okay, I think Klaus, maybe you, no, who is the next one, Klaus or Irena?
Yeah.
It's you. So come and be the person will, because there is no, the question is unclear, so I don't know, maybe later on.
Later, so we have to carry. Well, the presentation is uploading, right? So the presentation will give you now in the next 20 minutes is about one mission that is particularly interesting for polarimetry, and this is a polarimetry training course. Yes, we provide you some more details, and this is the Biomass mission. It's a mission in the ESA science program that will be launched hopefully in 2025. But I don't want to limit it to the Biomass mission alone. I also include a few slides on our other missions that are capable of doing polarimetry, especially on future missions, because we don't have anything at the moment. But most of it, 90%, will be on Biomass mission. This is a mission that is close to my heart because I was involved in this mission since, I think, 15 years now. Okay, so in a nutshell, Biomass is the ESA 7th Earth Explorer. So it's a mission concept in the Earth Explorer program. We are not following operational demands. We are not following missions that have already been developed in the past, where we mainly support operational services. It's really a program where we want to answer new science questions for which we did not have the data that is needed to answer these questions in the past. So we're looking at new technology, at new science. It's an interferometric, fully polarimetric P-band SAR mission. So it's the first P-band SAR mission that will go to space. And its science question is its main design driver is to observe forest height and forest biomass. And what I will do now in my presentation, I don't want to start with the system specifications too much, but I would like to start from the science questions because this is also how we develop these missions. So the underlying science questions of biomass was the carbon cycle and the fate of CO2 in the Earth system. You know that CO2, since we're living in the Anthropocene, we have heard it in the morning, CO2 levels have risen since years to amounts that are really critical, that are affecting everyday life. So it leads to global warming, it leads to all sort of extreme events. And we know actually quite well how much carbon is stored in the atmosphere. So this is numbers I got from the Global Carbon Project. So this is what is usually reported on the IPCC conferences. So we know more or less from measurements that the total emission in the atmosphere is 40.1 gigatons of carbon, petagram of carbon per year. Knowing what is in the atmosphere is not enough. So if you want to do something against this, you have to understand where does this carbon emissions or where does carbon come from, where are the sources, where are the sinks. So only then you can really take actions to reduce these carbon emissions. So we know, on the other hand, we know when we look on the lower part, so this is really now the lower scale, where we look at the individual contributions, at the individual sources and sinks. So we know, well, the biggest contribution is of course fossil fuel, gas, oil, and it makes about 85% of the emissions. And this is something we know very well. This is a highly regulated market, so we know the numbers quite precisely, up to an accuracy of 5%. Now, if we use on the second source, and that's the land use change source, it's a much smaller source. But if you look on the error bar, it's an error of 45%, so nearly half of the actual, or the uncertainty is about 50% of the actual number. The same is with the sinks. So we know that the Earth can also take up carbon, and the main factor there is the oceans and the land. The land carbon sink is the only natural thing that doesn't have any negative impact. So you can grow trees, you can grow forests. Forest absorbs enormous amounts of carbon, and they store it for long times. But also on these land use sources and on the sinks, we have quite high error bars. So the purpose of the Biomass mission is really to touch on these sources and sinks, and here mainly on the forest part, which are the biggest contributor here in terms of land use change and land sink. Forests are also important for other reasons. So it's not only to measure carbon. Forests have a major socio-economic effects. It is important as a source of material. For energy, for protecting our cities. We have heard it in the morning a bit. It's a very biodiverse area. Tropical forests are the most biodiverse areas in the world. So there's a lot of other aspects that are important of forests, and where maybe biomass can contribute some information. Now, the next question is, if you have defined this high-level science question, you have to start flowing it down to some requirements that engineers can work on, and that engineers can start building their measurement systems. So here we were looking at what are the high-level requirements to build a satellite. So the first one is, of course, we want to measure biomass. Biomass is basically a proxy for carbon. Half of a biomass is normally carbon. We want not only to measure biomass, but also to measure forest height as an additional constraint or source of information how forest changes. And we want to look at disturbances, so at cross takeout of trees. The crucial information need is in the tropics. Tropical forests store most of our carbon. 95% of the land use change flux is in the tropics. It's the area where most of the recross is, so half of the recross is in tropical forests. It's also the area where we know least. So basically in the Northern Hemisphere, there's a lot of systems that allow us to measure or infer the role of forests in the carbon cycle. In the tropical forest, there's basically no information. It is also an important implication because you really need a system that is sensitive to very dense forest types. And it can really give you the information about the densest forest. On the scale, the resolution we're aiming at a resolution that is effective to the scale of change, and there's typically a few hectares. So this is where people start to affect the forest by cutting trees and by taking out trees of the forest. Another question that was actually asked just before. We need these measurements wall to wall, so we want to have a continuous measurement, and it comes back to a question before: what is the benefit of PolInSAR to use measurements like biomass and height? It's really because you can get a continuous measurement, so it's not only sample measurements, but you get a continuous image. And finally, the accuracy, and it was should be comparable to what we measure on the ground, so about 20% of biomass that we would like to achieve. Now, how can you measure biomass from space? You measure a weight, a mass. This is something not easily done from space, of course. It's impossible to do it from space. It's even very tricky to do it from the ground. People are doing this sort of experiments. So they go in the forest, they cut down all the trees, they measure the weight of the tree. But this is, of course, not very sustainable. And it's also very tedious work, so you can do this on small plots, but not on a global scale. So already hundreds of years ago, so it's foresters started to develop different methods. So they measure the structure of the trees, and from the structure of the trees, they infer the biomass amount. So you measure, for example, the diameter breast height. From this, you can infer your diameter of the tree. You measure the tree height. You assume your tree is a cylinder. Then you estimate via simple density factor. You determine how much biomass is stored in the forest. And now this is something we can also do from space. So we cannot use weight, but we can measure structural parameters. So we have means to measure, for example, forest height. We have also other means. SAR is a very strong measurement of structure. So we can use these measurements to use very simple concepts like they've been done in forestry for decades. We can transfer to space missions. AGB, sorry, this is above ground biomass. Above ground biomass. Now, one measurement type that allows you to measure structure from space is SAR. You interact with your medium. If you remember the lecture of Carlos, you're in a side-looking geometry. You emit a signal to the ground. The medium that you observe will change your signal, will send it back, and you measure whatever comes back. Now, if you don't have any structure on the ground, if it's flat surface, most of your signal will be reflected away, so you don't receive anything. When you start to grow structure, when you start to grow trees or vegetation, more of this signal will come back to your sensor, and you can use this information as a structural measurement of how much structure you have on the ground. So this is the most simple way to do it. You can do this in polarimetry, but what you get basically is an image of your scene, and you can use this as a proxy information and then convert this with some models, and I will come to that a bit later, to biomass. Now, when we have two satellites, we can actually not only exploit the intensity data, we can also look at phase data. And the nice thing about phase is that it's a very accurate measurement that we can do with SAR systems. And we can use this phase data, or the difference between these satellites that fly in a slightly different position, to infer height. And because different polarizations are reflected in different layers of the canopy, from this, using simple models, you can derive forest height. So it's a second structure measurement that we can use to constrain our models. Now, the third one, and this is the most advanced concept, is tomographic SAR. It works in the same way as a tomographic system in a hospital. You take measurements from different positions, and you combine these positions. You build filters to take out or to measure each layer of your forest. Of course, from space, the accuracy is not great, the resolution is not great, but at least you get in tropical forest 3 or 4 layers that describe your forest structure in more detail. And with the biomass system, we would really like to exploit all these 3 measurement concepts. Now, choice of frequency. An important question when you build a SAR satellite is which frequency should you choose? The main driver here is, and it was briefly explained before, your wavelength, just as a rule of thumb, you're interacting with your medium, and the elements of your medium you interact most are more or less in a similar scale as your wavelengths. So if you use very short wavelengths, if you go to X-band, for example, wavelengths of 3 centimeters, you will interact with elements that are in the centimeter range. So, for example, leaves, small branches. So you will see, if you take a normal tree, you will see the leaves and branches of your tree, the top of the canopy. Of course, most of the forest is not in the leaves; it's in the stems. So you will have to go to lower frequencies. You can go to L-band. You get more sensitive to the trunk and the big branches. But really, the ideal case here is going to P-band, where you're really sensitive to the heavy trunks and stems, and they can also penetrate. So you're not affected by leaves. So you can really penetrate into the canopy. So the choice of for biomass was P-band, but there was another reason to go to P-band, and that's coherence. Now, if you want to interferometrically combine measurements, if you want to do INSAR processing, you need to make sure that your system is really coherent, so that nothing changes on your system, because otherwise you get decorrelation, you cannot combine the measurements. Now, when we build satellites for interferometric purposes, there's 2 strategies. You can have two satellites flying in constellation, taking the measurements at exactly the same time. So you make sure that nothing between the measurements have changed. Of course, this is programmatically not easily to realize. It's very expensive to build two satellites and to fly them at the same time. For Biomass, for example, this was not possible. So we look at repeat path systems. When you do a repeat path system, you're affected by temporal decorrelation, and you try to minimize that. Now with P-band, I said before, you're sensitive to the big trunks, which change less than, for example, the leaves. And there you can work with repeat path interferometry to retrieve information. And this here is an example. We did an experiment we did in Sweden. It's a boreal forest site. It's about 300 tons per hectare, so it's actually quite dense biomass domain. There's a big tower there, 30 meters tall. There's a P-band antenna on top, a C-band and an L-band antenna, and they make measurements every 15 seconds. And we were looking how the coherence, by combining all these measurements, how this coherence change with time. So we're taking one measurement, and then we're looking at after 1 day, after 2 days, how fast we lose our coherence. Now, if you look at a C-band, the yellow line, you see that after 1 day, even less than 1 day, after a few seconds, you lose your coherence and you cannot do any tomography, any interferometric processing. Of course, this is a vegetated area, right? So this is very special to forests. When you go to L-band, is this blue line. You see that you also lose your coherence. You're a bit more stable, but you lose your coherence also after very short time. So only when you go to P-band, you have the stability that you can combine your images in a repeat path system over a forest ecosystem. Huh? So therefore, P-band not only good in terms of penetration in the forest, sensitivity to biomass elements, it's also very important to allow interferometric processing. So the Biomass mission in a nutshell. So based on this requirement, we started to build a satellite. It's a synthetic aperture radar. It's polarimetric. It's a P-band SAR. It has 6 megahertz bandwidth, which is very short, and I will come to that on the next slide. It's a single satellite operating in a polar sun-synchronous orbit that we get really access to all the global forests. It has 2 mission phases. So the main mission phase is the PolInSAR phase, which is run through most of the mission. At the beginning of the mission, we also have a tomosar phase. It's an experimental phase where we want to try these tomographic processing techniques, where we will do 1 global coverage. And after this 1 global tomographic coverage, we will go to the PolInSAR mode and we will observe in repeated observations through the rest of the mission time globally. It has a multi-repeat path interferometry concept. So I said it before. We will take not only 2 measurements. So for interferometry, you typically need 2 measurements. We have 3 measurements, and this is one reason is as an insurance. So if something happens to one image, there's always another backup image that we can use. But it also gives us some diversity in the baseline. So you need different positions of the satellite, give you different sensitivities. And having these 3 passes give us this baseline diversity that allows to access different forest densities. And the repeat cycle of the satellite is 3 days. So after 3 days, we come back to the exactly same position and observe it again. And the lifetime of the mission is 5 years. So we get about 7 or 8 global cycles that allow us to look also at change. As a number, so it's really, we are currently at the end of phase D. So the satellite is currently put together and built. It's actually now we're in the testing phase, testing all the subsystems. You see here the platform, it's quite a monster. It's 4 meters tall. You see the reflector here. It's like an umbrella opening up. Just to give you a sense of the size. So this is a 12-meter reflector. The area is about 100 square meter, a bit more than 100 square meter. So it's really a huge piece of structure we will send up to space. You have here some technical numbers for those who are more inclined to SAR engineering. There's only 2 numbers I would like to point your attention to. One is the resolution. So the resolution, we are limited by 6 megahertz bandwidth, and that impacts the resolution we can achieve on the ground. So for Biomass, the single look resolution is 60 meter times 8 meter. You've heard it maybe before when you were in the room. We are affected by speckles, so we have to multi-look these images. So the effective resolution we deliver our level 1 products will be about 50 meter sampling. And this will give you 6 looks, which is not great, but it's something we can start working on. When we go to level 2 products, so the higher level products, biomass, forest height, then we move to 200-meter resolution to achieve the accuracy we need. The second thing is the swath width. The second characteristic is the swath width. I would like to mention in particular, it's a very narrow swath, despite this is a big structure, it's a 12-meter antenna, one of the biggest antennas we have in space. Everything in SAR scales with the wavelengths. As we use P-band, a 12-meter antenna is still quite small, on the smaller side. So this only gives us a swath of 50 kilometers. With a swath of 50 kilometers, it's very difficult to achieve global coverage very fast. You need bigger swaths. So what we are doing is we're doing a lot of tricks with the orbit. So when we observe an area for 3 times, we will roll the satellite slightly to observe a different area, and then we will even do some orbit maneuvers to access new areas. So there's a lot of playing around with the orbit in this mission, and that will allow us to acquire global data within 9 months. So you have to wait 9 months to really achieve global coverage. I'm mentioning this because this impacts a bit the way you can use this data. You have to think if you're, for example, in India, you acquire data or you cover India only within 9 months, you will have a rain season, you will have a dry season in your data sets. So it's very difficult to create global maps out of this data. You have to correct for all these environmental factors. And you don't have, I mean, typically what you do, you take long time series like for Sentinel or for NISA, you have a long time series every 12-day data set. You can average, you can eliminate data that is not optimal. For biomass, this will not be possible. You have one snapshot in 9 months and it will contain all sorts. So if you build a map of a continent or a subcontinent, you will have all sort of environmental factors playing into your map, and you have to algorithmically or from a processing point of view correct for these things. For coverage, we systematically cover all the areas that are here in red. So this is all areas where there are trees and there is forest. We will also cover the yellow areas on the best effort basis. So this is to support desert applications and ice applications, which for P-band is also quite interesting. We even have some ocean windows here and the sea ice window here. Biomass is not really designed for these domains. I think our noise floor is not low enough to go over the ocean, but we said for the first, having a satellite up there that measures at P-band for the first time, it's worth to also look at these things to support science. Another important feature here is you see we are not observing in North America and Europe, which looks a bit strange for European mission. But over these areas, the US military is operating a space tracking, missile tracking radars. So it's military material. And they are operating in P-band and they are fearing that we interfere with them. So they were not allowing us to operate our satellite over these domains. But in these domains, actually, I mean, the information is already quite rich. We have a lot of information there. We have other sensors that can measure biomass in these domains. So it will not harm our science case. For India, also a very specific case. We have some restriction with your launcher system. The Indian launcher system is having a termination control operating in P-band. So if anything goes wrong with a rocket launch, they send a signal to the rocket that destroys the rocket. And this signal is sent in P-band. And they feel that we interfere with their launcher operations. So they were asking us not to operate the system whenever they launch a rocket from the Kules Karapatam launch site and from the Satish Dhawan launch site. So 3 days before a rocket launch there, we are not allowed to operate in the vicinity of the launch site. From the launch time up to the successful completion of the launch, we are not allowed to operate in this bigger window here for security reasons. There's about 1 launch, I think, per month now, so it will not affect us too much. We will maybe lose 1 or 2 days per month of data over this domain. But of course, the Indian launcher system is very successful. It's very competitive. So we will see an increase of launches over the next years. I'm afraid. I mean, I'm lucky for you, but afraid for the Biomass mission. So we might lose a bit more of data there. But this is something we cannot influence, unfortunately. So the biomass products, I mentioned it already. So we measure above ground biomass, we measure canopy height, and we measure forest clearings. The resolution of the product is 200 meters for the first two, and the higher resolution for the forest clearing product. And we will provide one map every 9 months. So now the question is how to come up with these products. So if displayed here in English, we were taking over the local national park. It's a national park in Gabon, so it's on the equator in Africa. It's very dense forest, above 300 tons per hectare. You already see this is a polarimetric, is a Pauli image. So you see in red HH plus VV, which gives you information, for example, about double bounce. Double bounce is typically locked to the ground, so you have your wave comes to the ground, it's reflected by the trunk, and it's reflected back to the sensor. So these red pixels here already show you that you penetrate to the ground with P-band, even with intense forest conditions. Then you have in green, you have the cross-pole. Cross-pole is very sensitive to structure. So everything which is very dense forest is here in green. And then you see in HHV is specular reflection. So you see everything here, which is basically grassland. You don't see, you're close to noise where it's dark, and that answers one of the questions before. Can we use this also for agricultural applications, for example? In principle, yes, but you need the right frequency. So at P-band, this is dark, you don't see anything. Now, for this, you already see you can derive some information, but now we also have to quantify that, and we have to put this into numbers, into biomass and height measurements. So the most simple way is you build a regression model. It's not the most elegant way, but it's a very simple way and a very strong way. And I think 80% of the papers you will find in literature deriving biomass from SAR data are using this sort of regression approach and model the other way. So what I've shown you here is we have above ground measurements, above ground biomass measurements on the ground on the x-axis. We have here the backscattering coefficient in HV, so in cross-pole. And these are 3 different campaigns. So each color is a different site. So we have a site in Sweden, in northern forest. We have a site in La Selva, tropical forest, and another site in French Guiana. So it's a dense tropical forest close to the Amazon, or of the Amazon shield. And you see each point is basically a measurement on the ground compared to the satellite. And you see there is a very nice relationship. It's a nearly linear relationship if you compare HV backscatter channel to ground measurements. Now, but you also see that there's a big scatter around this. So this is mainly environmental effects. You have submerged effects on the ground. You have standing water. You have different structure elements. So all types of topography. So all type of elements that alter your relationship. And it's I mean the accuracy you can achieve with a simple regression model is limited. The other thing which you have to be aware of, and this is very important, is that each forest type will give you a different regression. So you have the forest, so the 2 tropical forest sites that look quite similar, but then you have the boreal forest that looks that gives you a complete different regression. So you cannot, I mean, you can use this regression analysis on a local scale, and you find a lot of people that are doing this. But if you scale this up to regional, you're already getting into trouble. If you do this globally, you will fail for sure. So you have to do something more intelligent. Sorry? Well, it's structure for sure. I mean, we know, for example, this boreal forest, they are like Christmas tree plantations, so there's all very organized forest, whereas in the tropics you have very chaotic structure. It can be the ground signal, for example, that the type of trees, it's how much you penetrate to the ground, if you're influenced by ground scattering or not. So there's all sort of different factors that play in here. So I have to rush a bit. The second measurement that we use is forest height. So I explained if you have 2 different positions, you can measure height by interferometry. You might know this from deriving topography, topographic changes. So we're using this as well for the biomass mission. And the nice thing here is that each polarization will be scattered at different levels in the forest. So you can use this polarimetric, interferometric information together with some simple models to derive forest height, and this works actually quite accurately. So up to 20–30% of error you can derive forest height with this information. And last but not least, we will use the TomoSAR, and this is just an example to show you the potential of TomoSAR. This was an experiment again in Parakou in French Guiana. We took 7 images of a tropical forest site, and here you see the transect. So it's a north-south transect of the normalized backscatter intensity at different polarizations, so HV and HH. And already here you see again, with P-band, you penetrate to the ground, especially in the light polarizations. HH, the main scattering contribution is locked to the ground. HV is scattered in the canopy. So by combining this information, of course, you get much more detailed and much richer information about the forest structure. How are we using this information? I think there's a lot to learn from this. We compared this data set, this tomographic data set, to ground observation. So a similar plot as I showed before. Now, if you take one SAR image as you will get it, looking at the HV channel, so HV cross-pole channel, you compare it to the ground observations, you get a correlation of 0.18. It's not great. I mean, you cannot do a lot. There's a lot of scatter around it for various reasons. So using only one image is very difficult. Now, if we go to TomoSAR, we can split it up. Actually, we can build different layers. So we can get a layer from the ground. We can look at the ground scattering. We can look at the scattering 50-meter height, and we can look at the scattering in 30 meters height. And if you look at the correlations again with the ground plot, you see how your correlation starts to catch up. So you see your ground is not correlated at all with biomass measurements. Of course makes some sense. But then when you look up in the canopy, so where all your biomass is located, then you see how you start to get a correlation between the biomass measurement and your backscatter measurements. Now, how can we use this? We have tomographic only at the beginning of the mission phase. So we were thinking a bit: can we combine interferometry and intensity measurements in a consistent way to derive or to get a better estimate of forest biomass, so that we don't end up here in this condition where we have no correlation. And the idea here was what I would call the Biomass tomography. So instead of, just recall that during the PolInSAR phase, we don't have 7 images, we have only 3 images. So we are a bit limited with the data we have. But still, with the data, we can do quite a lot, and we can we can notch out the ground. So we do something like we do in tomography, where we extract the information from different layers. What we do here is we don't extract information from different layers, but we use these 3 images to kill the information that comes from the ground. So we build a filter that is basically 0 on the ground layer, and that maximizes our return on the vegetation layers. Now, by doing this, is the same example as before. So this is the single image case where we basically have no correlation. When we go to the TomoSAR, you get basically the best results, very high correlation. When you go to the ground notch data, we are not exactly there what we can achieve with TomoSAR, but this makes some sense. We don't have all the data, but at least we get close to it. So this is the idea that we are exploiting for the Biomass mission, that we use this ground notching technology to get access really to the elements of scattering elements of the vegetation layer. Now, all this data is not all the data, sorry. All the processors are open source. So it's the first mission at ESA where we decided to make available all the algorithms and to share it with the community. You're free also to branch off your own branch and start playing around with it. You can even submit changes and we will review it. And if it's beneficial, we'll enter the official Biomass processor that we run at the agency. It's currently in a bit of a shaky state, so we're currently trying to improve it and to make it more accessible. But I think in 3 months, we should have all the algorithms available there. Summary: Biomass was proposed in 2005, so nearly 20 years ago. The implementation of the satellites, the real building of the satellite, started in 2015, and we are working towards a launch in Q1 2025, Q4 2024, Q1 2025. This is currently under discussion. The Biomass will be the first P-band SAR and the first systematic radar tomographic space mission. So it's a true Earth explorer. And there's a lot of unknowns at the moment. So we have only 1 or 2 campaign data sets where we can really test our methods. So there's a lot of unknowns and exciting science ahead of us. It's the first open source Earth Explorer, and I really invite you to contribute to this mission by looking at the algorithms, by improving them, and by working with them. And of course, it's a mission that will not only look at biomass in forest, it will also look at deserts, and it will also look at ice sheets, topography below forest. So there's a lot of complementary information that we can retrieve. Now, 1 minute. Okay, one more minute. Very briefly, I don't only want to talk about the Biomass mission. The Biomass mission is our main mission when it comes to polarimetry, but there's actually more missions here that are quite relevant. Sentinel-1 is, well, most of you know it is a P-band SAR. It's an operational, operational workhorse mission at the agency. It's really a mapping monster. It's not polarimetric, it only has a like pole HH-HV or VV-VH, so it's a dual pole mission, so it's not really polarimetric, but you can still start to play around a bit with polarimetry. The reason why I mentioned Sentinel-1 is we are currently working on the next generation of Sentinel-1 that should be launched in 2032. And this mission will provide even better capabilities to map the world in higher resolution, but it also has a quad pole capability there. So it's really worth to start working on polarimetric data, because this is something that will come. And one more mission I would like to work, also mention in the context of Sentinel-1, is another Earth Explorer mission that was selected recently. The mission is called Harmony. So Harmony will have 2 passive companion satellites flying with Sentinel-1. It uses the signal from Sentinel-1, so it's not fully polarimetric in itself. But when you move from a single satellite system to a bistatic configuration, you also rotate, or the signal you receive is rotated. So you get some polarimetric information also from these companion satellites. And this is something that is really new. So we know how this works over flat surfaces. We can estimate that. It's a bit less known over other surfaces. There's a lot to learn still, and a lot of work to be done still to understand what we're actually going to measure with this system in a polarimetric sense. And last but not least, Roselle, another mission that is launched, that is also launched as part of the Copernicus system. So it's very similar to the Sentinel system that you might know, but it's working in L-band. So it's a new frequency. And also important to note, it has a quad pole mode, so it can offer quad pole observations. And the launch of this mission is expected in 2028, so this will come a bit sooner. So summary, final slide. On either side, so the SAR mission capabilities are evolving very fast. We are providing operational systematic access to polarimetric and multi-frequency observation in the near future with Roselle, with Harmony, and also with Sentinel-1 next generation, and with Biomass, of course. I think it's exciting times for SAR research. There's many of first-kind research questions to be answered. Biomass is the first P-band SAR in space, the first time we systematically acquire topographic data. Harmony is a passive companion with some great potential to enhance the C-band capabilities that we have already at hand. And of course, all these missions have an open and free data policy, so you're invited to work with this data and really to contribute to our science and development. Thank you.
So I have 2 questions, basically on the instrument side. So whether the fourth choice of 434 5 megahertz frequency and 6 megahertz bandwidth at P-band. So how do you perceive the impact of that radio frequency interferences? Is that band clear, or
it's this is a very good question.
Yeah.
We have only a secondary allocation. So there is other primary, for example, amateur radio is using this frequency band. We have wind profiling radars from the ground are using this frequency band. So there will be interferences. We know that there's military radars around, which we see very clearly in L-band at the moment in other missions. So we are not protected against this. With 6 megahertz, we're very vulnerable. We cannot easily filter out. When we start to filter out, we lose basically most of our signal. So this is something, yes, we have some filters built in, but there's a risk for losing data by RFI, for sure.
So do you plan to take that in the ground processing itself?
It's in the ground processing, yes.
Okay. And the second question is like regarding the choice of noise equivalent sigma naught of minus 27 dB. So I believe it's for forest applications, that's a good number, but what about the other applications? So whether it will cater to that?
Yes, so that, well, it was really, the mission is designed for forest application. It was the mission driver. When we go to other applications, for example, over the ocean, we are including some images, but we are aware that we might be at the noise floor, and we might not see anything, even over agricultural areas. If they're flat, if they're not rough surfaces, we might be in the noise floor, and then we don't see anything. But this is a price we paid because we said the primary driver is forest, and there we are safe, and everything else is a nice add-on.
Okay, thank you.
Operate only strip mode.
It's a very simple strip mode operation like ERS-1. So from a technological point of view, we go back 20 years. It's very simple. The beauty about it is it's very simple to calibrate and to process the data. So there's no advanced beamforming techniques there that make your life much more complicating on the processing side. But it was not possible. It would have been nice because it allows you to extend the swaths, of course, going to these advanced techniques. But we were limited by the size of the satellite. So we are already now on the edge, on the limit with this very simple satellite system. We are on the limit of what we can launch. And there was no room for any advanced concepts like beamforming or having different antenna types. So the next speaker I should introduce is Irena. Irena Heinzek is online, and I think Irena will tell you more about what you can actually do with all this polarimetric data that we will collect over the next years.
But she's not going to wait for a second. Welcome to this presentation. I'm sorry that I could not come in person, but I'm very happy that I'm still have the opportunity to give you an overview of what we are doing at the German Aerospace Center, but also at the university in Zurich, at ETH Zurich. So I'm focusing today on two main applications because I thought it's probably too much, or I have only 30 minutes and you're already delayed. So I thought I just focus on two applications, provide you a little bit insight what we are doing. So the first application is related to soil moisture. I heard already when I was listening, there are some questions concerning soil moisture. So the soil moisture that I'm showing here now, or the application, is everything is done in L-band, which is, I would say, a very, very decent frequency that can be used for soil moisture estimation. However, I can think also about that S-band could be also very good frequency, which probably will come soon. It's nicer, so next year. So I think also this could be a very nice frequency in case it is polarimetric that can be used for soil moisture estimation. Let me start with a very simple image in order to show you what kind of data do we have when we have SAR data. I heard already that you had some lectures about what polarimetry is and what SAR is. So that's great, but just let us summarize a little bit here. So what you see in a normal SAR image, and this you can see here, this is now a very high frequency in X-band taken from an airborne system from DLR. And what you can see is in principle structure, you can see intensity. So this is normally what we could use when we have a single channel SAR, as for example here, only the VV polarization. If we have now, if we are adding, let me say, polarization, and this you see here now, in red, green, and blue, in this case HH, VV, and HV, then we're also adding information. So it's not only adding colors, but each of this color has also information content. That is not possible to be seen before when you have only one single polarization channel. And what are these information? These information are information concerning the scattering mechanism that we have. So for example, black area is forward scattering, blue area surface scattering, red area dihedral scattering, and green areas, which you can see here, are volume scattering. And only using these different scattering mechanisms, right, we could already have a view of what kind of scattering mechanism we have. and what is very, let me say, dominant for each of these specific area. Having this in mind, the main idea when we are looking for soil moisture is, in principle, what we like to do is to characterize our soil. And our soil is always, let me say, a part of, or seen, let me say, with the radar or SAR, is mainly two parameters which are important. The one is the soil moisture itself, so the water content of the soil, and the second parameter which is important is the surface roughness. So this is always, let me say, combined in a signal when we are looking to SAR images over a surface that is bar. So a bar surface has always these two signal combined when we are looking with a SAR view to this surface. So that's already, let me say, one point that we would like, or what we need to unravel, if you like, really to estimate only soil moisture without surface roughness. So another thing is then what we have normally is not only this bar soils or bare soil in general, but what we have is always the combination between soil and vegetation. So normally over agricultural fields, we have always vegetation on top, but also if you look now to wetland areas where we have also grassland on top, or any kind of other surfaces. So mostly the natural surface, most of this natural surface, but also man-made surfaces are all vegetated. So this means what we need to deal with is a kind of different types of vegetation types that we have as a vegetation. So vegetation can be either very low when it's in the beginning of the season, where we have agricultural fields, where we start to have a seed bed, and then the plant is slowly growing until the end of, let me say, the season, where we have then very strong growth. Then after a while, we have even drying of the crops. And afterwards, we have again the harvesting, which means we're getting again back to something which is very, very low vegetated areas, but have strong roughness component. So the main idea actually is, in order to get soil moisture, is really to try to separate between soil contribution and vegetation contribution. And that's only possible, let me say, because this is only possible if you really have a model-based approach. So it's not only the polarimetry that is important. In addition, also a model is needed, which is in principle modeling the soil moisture. This means what we need here is a model of the signal itself using a forward model. And then at the next step, what is needed is in principle use this signal that is forward model to invert it with inversion model. And like this, we are getting then in principle soil moisture as a function of the signal. However, the model needs to be simple, right? Because if the model is very, very complex and needs a lot of input parameter or in situ parameter, then we have a problem, because the inversion is getting more imprecise, and this is also very difficult to invert a model that has not, let me say, equal amount of observable as well as also measurable. So there's a lot of models ongoing here. You see only is really just an attempt to have a small part of models that are available. So I think since 50 years or even more, people are trying to develop models to extract soil moisture, which is not an easy task actually. So, and this, what you see here now, these are only models which are looking for soil moisture over surfaces which are bar surfaces. So in principle, we could divide the soil moisture models into three parts. The main are the theoretical parts, so theoretical models that are available. Then there are empirical model, which are having an extension normally of the theoretical model. And then we have the extension, which is based on, it's model-based extension. As said, this is only a few amount of them that are here listed, and it's not really meant that this is a full list of models that are available. But just to show you a little bit the development that you have within also of time. I would like here, I was underlying one model, one theoretical model, which is a small perturbation model. This is one of the simplest model that is available where we have a very, very strong relation to soil moisture and less to surface roughness as a disturbance parameter. And this is because we are here assuming to work with longer wavelengths, as for example, L-band system. And all the other models, for example, the empirical extension and extension of the small perturbation model, and also are using, let me say, coefficients, empirical coefficient in order to do the extension in terms of the validity range of this model itself, in terms of soil moisture, but also in terms of surface roughness contributions. And the same is also true for the model-based extensions. Then there's also a lot of bunch of vegetation models, right? Because we are still dealing also with vegetation, as just said before. So also here we could say we have three kind of pillars. Which kind of vegetation models do we have? So we have theoretical models, which are very complex model and very difficult to invert. We have scattering decomposition approaches where we try to use polarimetry to decompose different scattering mechanism, as shown in the beginning, in order to be able then to only extract the surface contribution to invert then the surface contribution with the appropriate model. And you have also other approaches, for example, this semi-model based extension, where we use, let me say, in this case, we can use physical, but also numerical approaches, optimization processes in order to extend it. And potentially you're aware of, that's not the end actually of all this model development. We have also a lot of machine learning approaches in the moment ongoing, which are just using the sigma zero estimate in order to estimate also soil moisture. So also here a long and a strong development is ongoing. My focus here is on the physical based models and not so much on the machine learning part. Okay, but let us now have a look where we are going to. So my main approach here that I like to show you is going, let me say, having a model for bar surfaces and then using this model over bar surfaces afterwards, after we have done a decomposition. And a decomposition in principle is here meant using the middle part, which is a scattering decomposition approach, where we try to decompose the different, let me say, contribution that are which are appearing, let me say, within one spatial resolution cell. Let us start with a small perturbation model that is a model that is the basis that I'm using in my approach here. And the small perturbation model is a very simple model here displayed as a scattering scattering matrix that you see in the Sinclair matrix. And the Sinclair matrix can be written down in terms of mainly two elements within the matrix, which is our S and RP. And our S and RP are functions of the incidence angle and the dielectric constant. What we have in front of the matrix part, and this you can see here, is in principle our wave propagation, and in addition also our surface roughness contribution, which is Z. So that is in principle defined as a Fourier transform of height variations that you could have within very small roughness scales. Let us consider a little bit, when we look now to this kind of model, then we know we have roughness contribution potentially, and roughness contribution normally is something that is added within the HV polarization, which is here now in this small perturbation indicated as 0. So very low contribution, whereas we have only some kind of surface roughness contribution, which is in front of the matrix. So this depolarization is normally available in the HV. However, this is now in this part, as said, is only written down in front of this matrix contribution. However, the soil moisture content, and this is also very clear, is in principle then only in this matrix only have a relation to these two elements within the scattering matrix. If we now do a kind of, we are performing a ratio programmation. So if you do a ratio between the elements RS and RP, then what is becoming then in principle you have only, because both elements have the same roughness contribution, in principle it becomes independent of the roughness contribution. Like this, we could consider that using a ratio contribution here with the small perturbation, we are independent of roughness. And like this, polarimetry can provide observation in an observation space where we could separate really roughness from soil moisture, because this is the first step that we need to do. Okay, let us have a look. How does it looks like now, just using small perturbation model? If we have now here a diagram where we have the measurements, the ground measurements on this axis, and the estimated using now for different test size as seen here for different soil depths, the estimation, then we see using only the small perturbation model, we are getting a very flat curve. So the problem here really is that the sensitivity to higher values of soil moisture is very, very low. So this is because of the validity range that we have for the small perturbation model. The validity range is actually shown here as a relation between the soil moisture content, so the volumetric moisture content, and the Ks, which is the roughness contribution scaled by the wavelengths. And you see here very well that most of the parts, as we can see here, are really outside of our validity range and very, very low.
Mine I don't have, my friends I have, but that I should return.
Sorry, I think there's somehow, okay, perfect. Great that you mute yourself. Okay, so what you see here is what we have within the validity range is only very few, in principle, only one parameter for this specific two test site that has been here shown. From this point of view, what we like to do is this extension, as I was showing before. So extension in order to extend the validity range. This is done here very simply using the XPREC model that has been developed, which is a model-based extension. Let us come back to the Bragg surface. If we now consider not to have anymore the scattering matrix, but let us consider to have also the depolarization that we would like to investigate, and the depolarization between the two parameter, the S and the P elements in the scattering matrix, is in principle here on this part where we can see how strong are these two elements really polarized. And using just now the Bragg surface, it is clear that this one is very strongly polarized, where we have a very high coherence between HH and VV. So from this point of view, this element in the Bragg's case is in principle 0. So it has an advantage. So it's a very simple model. So therefore it's very easy to be taken. But as I said, it's not very realistic for surface roughness contributions of natural surfaces. So how the extension is now made is in principle using nothing else as seen here on top, is in principle facets, a uniform distribution of facets, which are in principle simulating the surface roughness that we can include then into the model. And this is in principle here varied by our parameter, which is called beta. So like now we are getting also two elements which are important in order for soil moisture estimation. The one part is to include the HV contribution, and the other thing is that now HH and VV coherences are not anymore 0, but allows also to have a depolarization, which we can then estimate. So the advantage is with this one, we can extend a little bit the validity range in terms of surface roughness, but also in terms of soil moisture. The disadvantage is in this model really strongly, it's very, very strong sensitive to any kind of small vegetation cover already. If you go now to the results, we can see here again for one of the test sites that I was showing before, or for both of this test sites, you see now we have here the measurements of the ground measurements, again against the estimated measurements of volumetric moisture using the XPREC model, and we see we're getting a little bit closer to what we would like to see, mainly for depths that are lower, which is between 4 and 8 centimeters, as can be seen here. The ones that are a little bit closer to the surface, we see the relation is not so strong. It's still, there's still the relation, but it's a little bit weaker. And you see on the other side, this is now just an image of fields where we could do in principle this kind of inversion. You see most of the fields are not being available for this inversion because, as said, we have very strong vegetation content here. So every field that is very reddish, or in every field that is very bluish here, these are the area which are reaching the maximum of the spectra, and like this we are not able to invert. So only the fields which you see here, which have a variation of soil moisture, these are the fields which we could really potentially very well invert. However, still said, this is only for bar surfaces, and now the part parts is coming that we would like to show you at least one of the approach, even though, as said, everything is still on research, but this is one of the approaches that we can propose in order to do, let me say, soil moisture estimation under the vegetation. Say, let us consider to have a signal, and this signal is has a contribution of surface, dihedral, and volume contribution. So it's the kind of mix of several things that the same as we have seen already in the SAR image before. So the main thing, what we like now to do when we can really distinguish them, because when we are using polarimetry, we can do a kind of model-based decomposition, or even eigenvalue and eigenvector-based decomposition. But this idea here behind is a model-based decomposition where we try to model each of these components after the Freeman-Durden approach. So using the Freeman-Durden approach, we are having then in principle the signal, we have the vegetation, we like to extract the vegetation, and then what is remaining are in principle two ground contribution, the one which is direct surface contribution, and the other one where we have a ground contribution plus the vegetation contribution where we have the bounds also on the vegetation part. As said, so from the total signal, we are extracting the vegetation part, and then we are leaving, or we are left, let me say, with the soil part that is here seen as a combination. So like this, we have in principle two elements which we are using. On the one side, we are using a model-based decomposition to extract the volume. And on the other side, we have now an eigen-based decomposition where we are using, in principle, the ground contribution in order to invert for soil moisture using the approach, the X-Bragg approach that I was showing before. This has, therefore, we are calling it also hybrid polarimetric decomposition, and it has some advantages because what we can do now, we can constrain a little bit our vegetation. So which means we would like to, we are in principle defining the vegetation parameters a little bit like this. We can have a little bit of variation of what we are seeing. It's not only a random volume, but it can be also, let me say, kind of different other parts where we changing the shape of the parameters. And on the other side, as said, it's a constraints here for the surface parameter estimation. Okay, let go a little bit to data and to see how we can now see how accurate these data or this decomposition is. This is now done on a ESA supported study, which is the IGRISAR 2006 campaign. This data are available also over the ESA portal that you can download, and also the ground measurements are available and you can test it by yourself. So what you see here is a soil moisture map from April 19, and I have here a bar which is in principle showing the date of the estimation. We have soil moisture estimation here from the ground, from in situ soil moisture stations, which are placed in the ground and have a really over 3 months a strong data logging of the soil moisture changes that are appearing. We have done this in 25 centimeter depths, but also in 5 meter depths. And you see, and what you see also is a vegetation curve. So this is in principle the growth of the vegetation as a mean value here, the maximum vegetation height that we could observe within the time frame here on this IGRISAR data set. And the data is coming, as said, from April until July. So if you go now to the second one, we see we have less soil moisture. So in the beginning, in April was higher soil moisture values, now it's less. Everything is related to the first date. So therefore now it's getting bluisher, so which means less and less soil moisture. And then you see here now at the end, we have even less. But this is now just a visual inspection. So what we normally do in this domain, we always do kind of scattering plots where we again have the measured data. So the measured soil moisture against estimated one. And here you see now the same dates for April, June, and July for different crop types: sugar, beet, wheat, rape, and corn. And you see everything that would relate on this very curve, not curve, on the line that you see here. This is a zero error line. And the dashed one is in principle the 10% error line in terms of RMSE. And you see a total RMSE independent of which of crop type we have is around 6. volumetric moisture content. In June, we know the soil moisture is less, and you see the RMSE for all, we have a stronger clustering here now, is quite similar. And for July, we see again, it's even less soil moisture and the clustering. It's also on a different part. And here we see we're even less in terms of RMSE is much smaller. But this you can also play, this game you can play also for each crop type separately, if you like, in order to see really what are the differences in terms of estimation error. So however, we think then estimation error less than 10% is something that can be still regarded as something that is very usable. However, everything that is above 10% is probably very difficult to be measured and then also to be used for soil moisture estimation. Okay, here probably just to say also, these are now really the results using the decomposition approach plus the X-Bragg model in order to invert this. And over this time frame, you see it here just now for rape. Rape is still very short, but then it's really strong vegetated over this time in June, and in July you say it's already going to dry out. Also here the crop itself. So from this point of view, we have really very high vegetation, and this could be easily, or not easily, but it could be extracted. Okay, what you can do in addition, also using now time series, using polarimetry is not only soil moisture estimation, but you can also do kind of classification in terms of where, in terms of defining what are the changes occurring within, let me say, agriculture fields. This is now a different test site, which is close to Munich. It's called CropX14. This data set is unfortunately not available over the ESA portal. This is something that has been acquired by the DLR sensor internally. However, what you can see is for each of the dates here from May to July, you see we have some very, very strong changes. Everything that you see here colored are RGB Pauli images. And you see already, if you just look to this field, that we have strong changes from greenish going to reddish, so dihedral scattering, and then going back to blue, which means what we have here is then harvesting at the end in July. However, the fields, as said, so we had also some ground measurements, and we could see really, or we could observe how strong or how high the crop is growing and how strong the changes is. However, this is an approach that has been published by Alberto Alonso. He was developing an eigenvalue-based approach in order to define changes, and this is now here plotted as a decreasing contribution in terms of dates, and also increasing contribution also in terms of intensity. So all the colors are again based on the different scattering mechanism that we have, and the strength of the colors is in principle contributed to how much change occurred. And you see now for these different color codes, we can very well see that in April and May, we can very strongly observe plant growth. In this, in June, let me say, in June, in principle, we see that we have very strong fruit development. And then in July, when the plant starts to dry out, as we have seen it also before, we see it also very strongly that we have a decrease on contribution in terms of intensity. And here we have on this part, this is a contribution, which is an increase contribution in terms of intensity. So just to show that also time series are very valuable to be observed. Let me very shortly go now to the next step, which is the snow depth. So it's my second part of application that I just shortly like to show. And the question here for sure is, so yeah, probably I should also to mention that I tried now to separate. So my first application is really based on fully polarimetric data. And the second one, I thought it would be great also to show what dual pol can do, because also, as it has been just before explained, we have a lot of sensors which are dual pol sensors. But also here, we are able to do something if we choose the right polarization combinations. So my parameter here is snow depths, and the question is, why do we need snow depths? So probably you are aware of the one parameter which is very important is snow water equivalent. Is a very important parameter. The snow anisotropy is important, but also fresh snow in depths. And all of these is important, let me say, for a very different bunch of applications that we would need for hydrology, vegetation in general, climate change, right? Risk management like avalanches, flooding, any kind of weather forecast, but also for, let me say, for the animals that we have here from the habitat, and also for traffic monitoring. Okay, I'm now focusing on one particular test site where I would like to show you some results out of it. And this is the Great Arlech Glacier, which is one of the biggest glaciers in the Alps in Switzerland, where you see it has a length of around 23 kilometer long, and it's covered around 80 square kilometer in coverage in general. However, what is principle ongoing in the moment is a very strong decrease of these glacier that you can see here. This is the middle part of the glacier, just that you see it. This is an arm, which you will see later on in the image. It's a little bit higher elevated, so therefore you see here quite strong crevasses. So these glacier is in principle going into this middle part. Then we have here more gentle slopes going down. And then here we have a third arm, which is also coming into this main part, which is actually called also the Concordia place. I don't see my slides. Yes, it's a Concordia place. And this is a part here, which is flowing down then the slopes. Okay, this is actually the images that you see. So we have a time series now in between 2011 to 2012. Every of these images is looking now in the HH polarization. And we see here again the three arms and the middle part. So the middle part we saw in the image very well. This is the arm which is higher located. This is with a gently slope, this two, and this part is going down down to the valley. And we can see now changing from November, December, January, which are the snow heavy, these are the snow accumulation. Let me say, a lot of snow is due to precipitation is approaching, let me say, and it's very cold weather. So this we see we have a very strong scattering coming out. This is in principle taken from the TerraSAR X satellite, which is in principle an X-band satellite with a wavelength of around 3 centimeters. Now, when we are coming back to April, in May, we see now that the glacier is becoming darker and darker, and you see it also here. Here is a part, which is a higher elevated part, is still remaining with high scattering. However, all the rest of the glacier already is starting to change the color with increasing, let me say, temperature. In principle, this is nothing else as what we can observe is wet and dry snow conditions over this area. Here, just an example again of HH for the winter image, and here we see it below for the summer image. So this is typically what we have when we're looking to signals. What is happening is clearly when we have dry condition, we have stronger penetration of the wave, even though we have X-band, and we get volume scattering. If we have now on the surface a kind of a water, very thin water area, or even if the snow is very wet on top, then what we are getting is mainly surface scattering. This is a digital visual model of the area that you see. So we are really reaching from a 500 meter to 4,200 meters, just that you get an impression of how steep really this glacier is and which heights it is located. Here you see now the entropy images, which is everything that we would expect. The entropy is higher in winter than, for example, in summer. And also the alpha angle is higher in winter than, for example, in summer, because we expect surface scattering, here volume scattering, and as I said, on the top, we have also multiple scattering occurring anyway, which is less prominent, let me say, in the lower image for the summer image. So scattering mechanism vary with snow, ice condition, but also with in general. So this is what we have seen in general over the whole area in terms of time, but also changes or is very strongly different between different areas within the glacier. Probably this needs also to be mentioned. What you see now is just in terms of values, what we have try to do is try to separate what is the accumulation zone and what is the ablation zone. So the accumulation zone means that you have accumulated snow, and the snow is staying there. Also, let me say in summertime, it's just changing a little bit the temperature, but still you have accumulated snow more than you have in principle melting snow. And then the lower part is in principle the snow where we have more melting ongoing as we have in winter accumulation ongoing. So therefore we have separate them, and these can be also seen now in terms of two curves, the blue one and the red curves. This is again only for sigma 0. We have a change over the areas. Here in principle we are looking now from August 11 to July 12, which is a whole year cycle and very well seen. So in the winter months, we see this is a little bit higher, and in the summer months, this is a little bit lower. However, also for entropy.
Yes, I think we have 1 minute left.
I see. Okay, so we see entropy and the alpha angle is the same. So we have also kind of variations here. I'm just going forward. The same you can also see within the years. So you have changes within the years in terms of this entropy, alpha, and this area. So what I like just to show you at the end is how to use copolarimetric phases. The copolarimetric phases or the copolarimetric phase difference, let me say, is nothing else as an element, let me say, of our covariance matrix that you can see here. And this is the parameter which we call CPD. This CPD can be now seen here. So the CPD provides us information, so which is a parametric phase difference, provides us information about, let me say, the snow depth, so the characteristics of the snow depth. And here you can already see that we have some differences depending a little bit also on the season, on the temperature scale that we have. However, in addition to the CPD, what is also needed is in principle a model in order to extract this information. And the model here that is used is in principle accounting for different crystal structures that we have. So just as a very general approach, and this crystal structure we can also model. So in principle is our it is in principle the degree of the anisotropy that we use in order to model our parameter. What we are assuming that HH is differently propagating in the snow layer as for example VV, and here you see now the modeled parametric phase difference that you see here in terms of several parameters, which are in principle the parameters of the thickness, the wavelength, the degree of polarization, and the frequency. I'm just skipping this because this is a sensitivity analysis of how this degree of polarization in terms of modeling is reached. What I like just to show you now at the end are the results and how we could estimate them using also ground measurements that we had there. So we had a total snow height estimated. What you see here now is from 2016 to 70 is our copol phase difference that you see here, and it's clear that for fresh snow we have an increase of the thickness, and for snow that is aging, let me older, what we have in principle the thickness stays actually the same. Here is our model based model that we are now doing with different shapes, let me say, of our crystal. This is a degree of polarization and the measurement that we have, and we see we have quite a good correlation, let me see, between the measurements in terms of thickness and the modeled value. And this is again depending on air temperature and snow temperature. And we can define certain areas where we see that we have compaction, but also accumulation. The same is now with 2011 and 2012, where we see we have areas of melting and again also areas of compactions. And this is actually also my last slide in terms of parameter, just to show that it's possible also to estimate snow thickness using, just as said, true polarization. This book has been already mentioned, but just to say also a lot of different other applications are also very well displayed here. And what is also interesting is we have also a code that is available. So if you download this book, then you have for each application also the code, and you can run your own inversion, let me say, or modeling part. So my take-home message really is the one was using fully polarimetric data, and this is really needed in terms of estimating soil moisture appropriately below the vegetation content. And the dual pol can be used, let me say, for snow depth estimation. And here important is to use, let me say, a combination of dual pol polarization, which are feasible also to have a kind of correlation, and are feasible to be used for the estimation using also a model in addition. Yeah, thank you very much. And I think that's concluding actually my talk today.
Could you conclude in 1 minute, please? Thank you.
I am ready already. Are there some questions?
One question, only one.
Hello.
Yes.
Just like when we are estimating soil moisture, we need to remove the vegetation component. And we were using this Freeman-Dodden decomposition for just removing the vegetation component. But what I think that since crop is a dynamic thing and it changes during the time, and at the same time, like different crop have different structure. So simply going with a simple decomposition technique for removing this vegetation, I don't think that that is going to be a great idea. So, like, what are your thoughts on this? And yeah.
Yeah, I agree. It's not so easy to do. So we have, as said, we have developed this very well on this agri-SAR crop. And this, I have to say, this is quite a homogeneous crop. So the surface is actually always staying the same. So the surface below the crop is not changing, or the only in terms of roughness. So the only thing, because if you have one is seed bed, everything is flat. So this is remaining the same over the whole season. What is changing, I agree, is really the height, and you need to be sensitive to the height, actually, to the volume itself. So therefore you have seen also, I started to have estimates where you have already quite of substantial vegetation there. So it works when you have already, let me say, a certain amount of vegetation there. For example, I started with April, where you had already 50 centimeter as a minimum on crop vegetation on this part. So it works when you have already vegetation, and then if you have homogeneous, let me say, development of the crops too. So sugar beet was quite good in this case. Wheat was quite good. I think I had also rape was also good. These are all the vegetation which have a very particular shape, let me say, in terms of vegetation shape. So all of them can be regarded, let me say, at the end as volume, random volume contribution. So which means a quite of homogeneous volume layer. In case where you have very, very strong, let me say, variances between in the growth stage between the different volume cases, I would completely agree. Then in principle, other approaches need to be considered in order to get the volumes well estimated. There's also other approaches which are looking for the anisotropic differences, so bifringal differences in crop. But for here, what you would need is not only let me say, the polarimetry, but what you need here is in principle the extension using interferometry. So in case of using interferometry and polarimetry in combination, like PolInSAR, then it is easier or is getting easier, let me say, to also estimate crops which have very, very strong differences in terms of the shape. I hope this answering the question.
Then just one question more.
No, there is no time.
Okay, thank you.
Maybe you can ask to our other experts later on or tomorrow. We had planned to make some nice interactive tutorial, but we have no time, so we will make it short. Anyway, Carlos and Armando will explain to you.
Okay. Okay, we are going to switch the whole system now. Thank you, Irena. So, as I have shown this morning, you will have all the material of the practical session online. So we are going to show again where you can access this information. You need to show this presentation, this QR code. Okay, perfect. So here you have the information. You can download the data. You will use SAOCOM data, so it's fully polarimetric. I mean, we were mentioning in this presentation that SAOCOM data was not accessible except for this data set. Okay, so you don't have continuous access to the data. So just for some particular data sets. So the data is in there. It's a high quality data. I have to admit the Argentinian colleagues have done a very good job on making available this data. So you will be able to see the different concepts we have shown all along this presentation. So also you have access to the different codes. So Armando is going to show you how to run this, how to make functioning the Python codes on the Google Colab. Okay, so you can run everything. So also before I forget, I have included the presentations of the tutorial this morning. So you have a folder there. So you have the 3 presentations on PDF. So you will have all the possible information we have presented today, okay, which is too much. So you need to digest at home. Luckily, we don't have a final exam, huh? So that's a good point. So, and we know, I mean, each time we give a course, that's a lot of material, but I mean, one thing is to attend a course, and the second thing, the ball is on your roof, because you have to go to the material, to slowly go into the questions, etc. Okay.
Okay, so I just wanted to say that when you go to this for the Google Drive, right? The materials. So when you go there and you download these materials, you see there are 2 Jupyter notebooks. Okay, you can make use of them, but if you want to use it in Google Colab, you have to. There is a presentation of Armando that is explaining how to use the Google Colab. So now we will not explain it, but you can do it later on. You just need to have a account, Gmail account, and then on Google Colab you can use it. But there is a presentation, so Armando will show you where and how to approach it.
It goes there, yeah.
So this is not the one you have access, because the one you have access more material. This is the personal copy, because we know it runs perfect. Okay, so that's just you will see some additional code. Okay.
So yep, thanks everybody. It will be very quick. I have to shorten 1 hour session in 10 minutes, so it is possible. Let's see how it goes. So I would like to open these slides here so that I think you should be able to see them. So the purpose of this practical is for you to experience a bit how to use polarimetric data. And in particular, we would like you to use Google Colab and Jupyter Notebooks. Why Jupyter Notebooks? Why Google Colab? I'll tell you in 1 second. Just telling you that, oh, this is not the latest version. Well, okay. Doesn't matter. So that part we cannot do actually, so we just need to skip and go for the rest. But you will find this code inside this folder that you have online. 1 second, it is coming up. And oh, this is a. I hope It's a very strange view. Let's see if I can reduce the size. Yeah. I think this should be a bit better, right? So you see the code is represented here. Google Colab you can get very easily. If you just go on your Google account, you need to open a Google Drive. So you need to go to your Google Drive, and then from there you will be able to open to connect to your Google Colab. Google Colab is not other than allowing you to run Python code, Jupyter notebooks from Google servers. And the thing that is interesting is that you don't have to download the data. The data can be in the Google Drive as well. So everything is in the Google server, the data that you have on your Google Drive, and the code that you see here. So there is no download, no need to install anything. This normally works very well with everybody. So that's why we use for education. But you may also decide to use it for collaborating with your other collaborators, because everybody that has this link can access the code, and so you can work on that together. So what you need to do in order to run this code, if you are not familiar with Jupyter Notebook, is to basically go on these places here. Where did this thing go up? Go on these parts that are called cells. So each one of these blocks is called a cell. And to run a cell, you have to go Control-Shift. So if you do Shift-Enter. So you go Shift-Enter, it runs that cell, and it goes to the following cell. And every time you want to run a cell, you just keep on going Shift-Enter. So you see this part here is marked down, is messages for you, humans. This part here is the code, is messages for the machine, but you have to write it. But this is what the thing that runs. This is the things that just explain what is going on. So before I start proceeding, I would like to acknowledge the data that you will be using, which are here. These are SAOCOM data, so you've seen from CONAE, from the Argentina Space Agency. And this data, the one that you have to use is this one, geocoded subset, as you will see also from the code. And these are in coherency matrix format. So you see, before you were, Carlos, talking about the coherence matrix, now you see it. So these are the elements, the T11, then the T12, and so on, all the elements T13. So the elements of this matrix that are there. You see this is a multi-temporal data set. In this practical, you only use one single image, one single time, but there is much more for having fun with. So we share all, you just can work with more than just the image that you see there. This is a little subset of a bigger image. The bigger image you can get from CONAE. I don't know if I put the link here. Actually, no, but if you Google, you will find a link where you can download other data from CONAE as well. This is not the only image that they offer for free, freely available. In Europe, we have an enormous amount of CONAE data that we can use. I don't think you may have access, but it's, you still have something for free from CONAE that you can use here. So let's quickly go to the code just to see what is going on. So when you are inside a cell, you just go Control-Shift-Enter, and we run that cell. So in the first cell here, we import the libraries, and so you know the cool thing of Jupyter or the Python is that there is a lot of libraries that somebody wrote for us. So you don't have to code all from scratch, but you can import these routines from other libraries. For instance, these are the classic one. If you want to add an extra library, you can also do it even in Google Colab. It's a bit more complicated, so we don't do it here. But anyway, what I want to say before finishing 3 minutes is that in order to be able to run this thing, you need to connect it to your Google Drive. You do it with this cell here. See, from Google Colab into Drive. These things here will mount your Google Drive into your Google Colab. If you don't run this, it won't work. And so if you do this thing, you'll see start thinking a little bit, and somebody says that it's connected. So, can I connect? You say, of course. And it wants you to put your password. This is not the password. This is I won't show my password, but you need to add your password, and you click allow, then you will be able to proceed. And you see, there are other series of things you can do in this code. There is a lot of comments here. So most of it will be, say, explained in these comments. Unfortunately, we don't have the chance to go and answer together some of the questions that I put here. You see, there's question there. We could have talked about, you go. We could have talked about this, but there is no time. But you try to answer your question yourself. If you have doubt on what they mean, what is the result, what we should be writing, drop us a mail and we are happy to chat about that. So I think I'm afraid I need to close it here. Let's go through just to see. So at the end, you will get the exercise will allow you to load data, which is what you do here. Then will allow you to plot a Pauli RGB. Remember, Carlos was talking about Pauli RGB. You will be able to do it here, so you can experience how it is to produce a Pauli RGB. And here we take a subset of the image, and this part here you apply the filtering we talked before. You do it with a convolution with a box. So the kernel is a box. You apply a box car here, and this is the zoom of the image. And then we delve a little bit on the statistics of this data. You see here the histograms for the intensity. And this, remember, Carlos was saying this is an exponential. So this is not an exponential here because we averaged. So this is a gamma distribution. But I think you talk about that, right? No, not the gamma, no. But anyway, so that's why it's not exponential. It's not that Carlos is wrong. It's that we averaged. Then this what we do here, Clopotier. Clopotier is the diagonalization. So you see, to do this, you have to use a for loop. If you're not familiar with this, drop a mail, I'm happy to help you understand what is going on. But we need to do it pixel per pixel because there is no. So it's complicated to use an exact solution. There are approximations that are good, but it's the simplest to understand it is by doing pixel per pixel and then do a diagonalization. This is the core of the routine, actually. All this code, this is the core line where you do this diagonalization, just one line. And at the end, clicks down so that you know when it's going to finish. And you have your final image where you plot the eigenvalues, and the first eigenvalues is bigger than the smallest one. That's good. And there is a dominant alpha and a mean alpha. And I think that's it. I think I have to close here. Otherwise, it kick us out. So if you have any question that takes less than a minute, please ask. Otherwise, we can also talk tomorrow.
np.int that you have used needs to be corrected in the code. numpy.int. It's a numpy version.
Yeah. Do you want to use NV or how this connects to NV?
No, numpy.
NumPy, yeah. How I convert from NV format to NumPy?
It's you have used np.int to convert a float to an integer, right?
Yeah.
That won't work in the new numpy versions. You will need to specify the precision.
I see. Okay, so this function, but because it's working now, I ran it.
No, because I downloaded and ran it, the whole thing.
With the version 10, so 3.9 is the current version, right?
Yes.
That's strange because this is running on the Google server. Maybe Google doesn't have the new version. But good point. No. So if it crashes again, can you let me know? Because this is not running on my machine.
No. I have ran the whole thing through. That's the only thing.
Okay, let's talk about it. If you show me the crash, then because I need to know for the future. But I think this is running on Google, so it's running. Very good. Questions? Okay. So thank you.
Yes, I think we can close here. Thank you so much for attending. I don't have microphone, but working. Yes, it is working. Thank you so much for attending our session. And if you have any other questions, I think Klaus will have another presentation tomorrow. And we are here also tomorrow. We are around. So if you have questions, please approach us. Thank you so much.
Yeah. I kindly request Dr. Avik Bhattacharya to present the mementos.
Thank you. Well, thank you very much, all of you, for this wonderful session. Thanks, Carlos, Francesco, Magda, Armando, and Klaus for being a part of this ESA co-located workshop. And I am sure that all of you have enjoyed it. They will be here around tomorrow morning or afternoon session. If you have any questions or would like to discuss with them, please feel free to contact them. And again, thank you very much for attending this workshop. Now I would like to call Professor Carlos Lopez Martinez just to have a small memento for appreciation. Thank you very much. A big round of applause.